There's an echo. I cannot hear you clearly. Yes, yes. Okay. I closed the other one. I think that's better now. Okay, okay. So please show my PowerPoint slide just by you, because I cannot. Okay, okay, that's fine. It's great.
Hello everyone, TEMS Talk present you a captivating topic of unmanned air vehicles, an aircraft without a human pilot on board with a ground-based controller, either remote controlled by human operator or autonomously by onboard computers. And these unmanned air vehicles are widely used in various purposes like target and decoy, reconnaissance, delivering cargo drones, also expanding to commercial, scientific, recreational, agricultural, and other applications like sports activities for fun, like drone racing. And last but not the least, research and development to improve UAV technologies. And that's why today we are having an eminent speaker with us whose research interests are in aircraft design techniques, aircraft performance, flight dynamics, autopilot, and design and automatic control of unmanned air vehicles. He is also an active professor at South New Hampshire University at Manchester, as well as the author of Design of Unmanned Aerial Systems and other popular textbooks, none other than Dr. Mohammed Sadreay. Wings of Pharaoh heartily welcome you, sir. And my dear participants, I request all of you to register at academy.wingsofpharaoh.in to get your participation certificates. Hello everyone, TEMS Talk.
Welcome you, sir. Most probably, I want to say few things throughout, not only in India, whereas from entire world, when people want to speak about aircraft design and when they want to step into designing, so they will be going for first name, that is Mohammed Sadreay, sir. So actually, that is a great opportunity. Right now, we are having to meet you over here. Thank you, sir. Thank you for accepting our invitation, first of all. I request the participants kindly mute your meeting ID, right? Mute the call and don't choose the present now option. See, it is only for the our presenter. So kindly don't click at the presenter option or don't unmute. So let's hear from the author of aircraft design, aircraft performance, and also design of UAV systems. Sir, welcome you, sir. I request Aishwarya ma'am to share the presentation so that we can go for the lecture directly.
Can you show my slides, please?
Yes, sir. Yes, sir. 1 minute, sir.
Good evening, everybody. This is Mohammed Sadreay. This is my pleasure to talk to you, and thanks for joining online to this talk. I would like to present a talk on a review on active research projects on unmanned aerial vehicles. So as you saw on the flyer, it was a short topic, but this is the better topic. So I would like to talk about 45 minutes, and I will review on the recent active research projects on unmanned aerial vehicles. As a quick overview, I will have an introduction why the unmanned aerial vehicles or drone or UAV or RPV, there are various names, are important. And then I will talk about, can you have the second slide, please? I will talk about 10 different
Sir, 1 second, sir. 1 second.
topics.
Sir, 1 second, sir. Actually, the slide is downloading only. So it is not present actually. So we will speak generally. So when the slide is ready, Aishwarya ma'am will be presenting them. Then you can go for the slides, sir.
So I am now on slide 2. Do you?
No, sir. The slide is not yet downloaded, sir. It is on the. They are downloading actually. It is taking little bit time. 1 minute time, sir. Sir, actually, before that, can you tell us how you have got this great books and other ideas, sir? How you have when you are writing that book, aircraft design, what you have in your mind, like how it will be focused for the students and others?
Yeah, that's a good question.
Yes, sir.
I am in this field now for about 10 years. And when I started teaching, I think about 11 years ago, I found out that there is not a good textbook on aircraft design. At that time, there was a couple of available ones, but none of them were good in terms of steps, concepts, deriving equations or examples. So I wrote my first note when I taught this course, I think about maybe 27 years ago. And then students were happy about that. And then I continued to improve that note and handout. And about after 10 years, it becomes a good, I think, manuscript. And I submitted to Wiley, and they right away approved that. So I thought that would be a help to students to follow this important topic, to design aircraft. And I'm very happy that you like that.
Yes, sir. Sir, not only our university, India's major university is following your book only for designing aircraft and other projects like UAV also. So once again, I would like to thank you that you have accepted our request and for delivering the lecture. Sir, now the presentation is on, so you can go ahead, sir. It is in the first slide.
So
yes.
Thank you. Can go to slide 2. I would like to talk about 10 different topics. And again, I will review them because we only have about 45 minutes. I will start about the topic of detect and avoid, which means UAV has to detect any obstacle and avoid any crashing. Then I talk about intelligent flight planning. Sometimes the UAV should design its plan intelligently. Also, another important topic is manned-unmanned aircraft teaming. How we can have a team of 2 or more aircraft, one manned in one side and another unmanned in another side, how they can do a mission together. Also, I go to formation or swarming flight when a couple of maybe 10, 15,000 even UAV can have a flight together. Another important topic is integration of unmanned aerial vehicle into aerospace. So how we can allow them to be in the air and space without any crash and any accident. Then I talked about a couple of important explains that they are about experimental results. Then I talk about unmanned combat aerial vehicles, a few of them. Also, I will talk about automated recovery, how we can recover UAV after flight. Also, I talk about fault monitoring, how they can monitor their fault, and also cybersecurity. Slide 3, please. In general, I believe we can you go to slide 3. Next slide, please. Yes, slide that's it. I believe there were mainly 3 revolutions in aeronautics. One was in 1903, when Wright brothers, they designed and built the first aircraft. Then it was jet engine invention in 1940s during World War II by 2 scientists. One was in Germany and one was in England. And the third one was unmanned aerial vehicles, UAVs. I think this is the third revolution in aeronautics. Slide 4, please. First of all, the application of UAVs are very much expanding exponentially, both in civil side and military side. Also, the number of UAVs are increasing significantly. We have lots of advances in wireless communication, in sensors, in micro electromechanical systems or MEMS. Also, all of those are making possible to have inexpensive small autopilot and UAVs. However, we have various challenges which are rising in front of designing and improving new UAVs. And I believe every year and every day there are lots of new research projects in different universities, industries, and also government agencies. Slide 5, please. Just a quick introduction in terms of number of UAVs. You can see here in terms of 2 groups of UAVs, one in hobby air area and also in one in commercial areas. In 2020, we have about 3 millions of UAVs for hobbyists. They want to just have a fun. On the other hand, in commercial one, which one we would like to have some income out of that, we have about 6.2 million, but these 2 are only in the US. However, always slide 6, please. Always we have different ways to improve UAVs from different aspects. For example, we want the UAVs to be lighter in weight, cleaner in terms of, let's say, CO2, quieter in terms of sound, and also stealthier, which means they cannot be detected by radar. We would like them to be faster, have more speed, safer, no crash, no accident. We would like to have lower cost in terms of money, longer range, both in terms of range and endurance, longer flight, and also every year we want to have a new applications. Slide 7. As an example, these 2 aircraft you see here, these 2 UAVs, they are Predator series family. They were designed and built by General Atomics Aeronautical Systems, and they announced on 2018, about 2 years ago from now, that they have a milestone of 5 million flight hours by the group of these UAVs. So these UAVs have mainly 3 versions, A, B, and C. Predator A has a piston engine, it almost retired. Predator B has turboprop engine, now it's very active. It has a couple of versions. For example, it has a Reaper, it has Gray Eagle, Sky Guardian. Also, the new version which will coming up maybe in a few years, it is called Predator C Avenger, which is supposed to have turbojet. So these have about 360,000 total missions. And also 90% of those were in combat missions. So as you can see, the UAVs are having lots of applications. Slide 8. In terms of how we can pilot a UAV, we have at least 5 ways. One is remote control, which means a pilot is on the ground and UAV in the air, and we can send command through communication system. Now, almost 90% of the UAVs are controlled this way in the USA and also in the world. Then we can go to the higher level of autopilot assisted control, which means the UAV can use its autopilot in part of its flight, let's say cruise. Then we have semi-full autonomy, which we give more autonomy to the UAV. Then we have full autonomy, which means the UAV can take off, climb, cruise, descend, and also land. And the fifth one, which is highest level of autonomy, which is intelligent flight, that something like a bird that can detect, it can change its flight plan, and also intelligently can survive. Slide 9. First, the research topic is about detect or sense or see. There are 3 words for this part, and avoid. In this case, we would like UAV to detect any obstacle, any other aircraft, and avoid any crashing in this case. As you know, it's very important to avoid collision. It is a primary concern of FAA, Federal Aviation Administration, for both unmanned and manned aircraft. At the moment, in the USA, we have a system called TCAS, or Traffic Alert and Collision Avoidance System. This is a primary system at this moment. However, it is not reliable now to allow UAVs to be part of that. Because if we add UAVs, there will be high computational requirements, which means we need to have a large computers around the world to process lots of data. So this is a black box now, and we have a problem here. It is not still saved. And we have also weight restriction for UAV, how we can add this equipment to UAV. It's not easy to do that. Slide 11. I took this picture about 2 years ago. If you go to a site called flightaware.com, you can see this. I selected Boston, which is, I live close to this airport. And you can see at this moment, it was, I think, about maybe afternoon. You can see maybe about 200 aircraft in that region. The green one are leaving Boston. The blue one are arriving in Boston, and the white one are just passing in this region. So you can see very busy area in this region at this time. So if we add UAV to this part, it will be much busier. So now we need to have a machine vision as an active solution, and we have to have a precision control to make sure that there is no crash between aircraft. So it's very hard. Slide 12. So the solution is to use a couple of sensors at the same time. One is accelerometers, 3 axes. One is to use magnetometers, 3 axes. Also, we need to use gyroscopes, 3 axes. Also, we can use conventional IMUs, which stands for inertial measurement units. And if we use all of those, along with cameras and vision sensors, we can reduce the challenge of navigation. However, we need to use some kind of state estimation to find out the location of the UAV. So in general, one of the solutions is to pair IMU and also vision sensors and also GPS to have a precise measurement of 2 things. One, in terms of full 60-degree of freedom of motion in the space or air, and one, find the other aircraft distance. That's also another important part. Slide 13, please. Now I want to cover 3 examples that right now are very active in NASA and Air Force. Example 1 is about an example of having 3 aircraft involved. First, the UAV or own ship was a Predator B, which is also called Icona. This is a remotely piloted aircraft, so there's a pilot on the ground to control this. And on the other hand, we had 2 intruders. One was FA-18, a fighter, and one was King Air. It is a GA aircraft. So these 2 were called intruder. They were going close to the UAV, and own ship was the UAV. And look at this. They were trying to have there were about 30 people involved in this project. So every day they had about 3 flights. 4 hours of data collection was done. And also in each encounter, they had 10 minutes. So they had to stay up about 4:30 a.m. and about 4 p.m. So about 12 hours of operation, about 4 months. So they tried to have about 500 feet of vertical separation between UAV and manned aircraft, and also 0.5 miles, half a mile horizontal separation. They had about 300 unique encounters. So the UAV was flying and they tried to close either fighter or GA aircraft, about 20 encounters per day. Just, you can see the command or goal was this. They asked UAV if the intruder is higher than you in terms of altitude, just descend. If the intruder is lower than you, just climb. So you can see it was very simple for this moment. It was, I think, 2018, this project. Next one was by Air Force. They had a group of one RQ-4 Global Hawk, as you can see in this picture, and then F-16 as a fighter, as intruder. So as you know, this Global Hawk has about a max speed of 150 knots. However, the F-16 has a stall speed around 135 knots, so it was very close to its stall speed. So it's almost stalling when they were supposed to fly one by one along each other. So this flight test was done at about 6,000 feet. And the flight rehearsal was about 8 to 16 hours of full teams, both pilots and also engineers. In this test, they tested about flight quality, performance, and sensors, all of those. Unfortunately, some data were junk because at 30,000 feet, so data link were not working very quickly and very efficiently. So they had some mishap plan. What happens if something happens by mistake? And they have to lock down everything and investigate. So if you, probably you know that when they wanted to, for the first time to test Global Hawk, I think about 2003 or like that, they locked down the entire part, some part of California, Air Force. And they asked nobody should fly in this region. We want to have this Global Hawk and just independently, but they didn't know what will happen. It is safe to fly without any pilot. And then they did that, it was successful. The third project, it is done, I think, 2017, this project by NASA. It was using a couple of UAVs. The goal was they tried to have a flight of UAV to a new area to detect only objects from different altitudes, let's say 10 feet, 15 feet, even 1,000 feet. They tried to have different classes of objects. They wanted to identify tree, pole, animals, buildings. And they had two types of controls, navigation system. One was GPS, which is very famous, and was their own system, PTAM, paddle, tracking, and mapping. They used both of those to make sure the UAV does not crash and does not collide with any other things. They had indoor and outdoor. So the UAV was flying inside a building, inside a hangar, also outside. And you can see they were about 95% successful. They used different type of cameras and sensors. And there were two group of NASA research labs involved. One was NASA Langley, and also one was Ames research, one in Virginia and one is Silicon Valley. So in general, they had tried to have also another first solo flight for the Icona, which is a Predator B UAV. It was equipped with detect and avoid technologies. And they tried to have this UAV over California and close to unmanned aircraft operation within the US National Aerospace. It was close to Mojave Desert in Edwards Air Force Base. They tried to enter Class A aerospace, also Class BE. So they tried to fly north and also try west. And they tried to change the controller between different traffic controllers between two regions. That was one of the first topics. The second one is intelligent flight planning. Another active research project is how we can plan the UAV intelligently. In this case, the UAV should be able to plan and also replan and replan based on the new situation to cope with undesired situations. They've used the advanced sensors with high quality and high level of computing environment and computers, and they use different type of flight planning algorithm. They try to just make sure how we can have intelligent planning. They also try to test their improvement on software and hardware performance, and think about how many lines of program is in there. Just good question could be for you to think about. In this picture, you will see two maps of the US. In the top left, you will see that there are about 5 circles. Each one is different aerospace, let's say A, B, C, and D, for example. In the lower right, you will see another part of the map for pilots. You can see the word prohibited P67. So this region, no aircraft is allowed to fly close to this region. So in terms of intelligent flight planning, they have to make sure that they know the surrounding in terms of the terrain, what is the mountain, hill around that, what are the other traffic, any other aircraft, what is my aerospace, I'm in A or B or C, because they have different requirements. What is the weather? Is it cloudy? Is it sunny? What is the temperature? Is there any restricted area close to me, like P67? Are there any obstacles if I'm inside a rural area, if I'm inside city? Should I be close to any building and tower? And also, where is my closest airfield in case I want to land? Where should I go? That should be part of the information for intelligent flight planning. So in this case, the UAV must plan the optimal route, which means how can I go back and what is the best way to move this mission to minimize the flight time and also the fuel usage, because we know we have limited fuel in the tank. So in this case, the aircraft will detect any incoming aircraft to prevent any collision. That's part of the design process. This is a very important active research project at this moment. The third one that I'm also working on is man-unmanned teaming. It's called MUMT, M-U-M-T also. There are various ways to team a manned aircraft and an unmanned aircraft, or more than one. Now we have lots of manned and unmanned aircraft, both in civil and also in military services. And the statistics are growing exponentially. Now we have thousands of unmanned aircraft, thousands of fighters, and how they can mix them together to have a more complex mission. In this case, we have safety of flight, also safety of people on the ground in the aircraft, and also the property of the people on the ground. We have to make sure about that. There were some incidents on unauthorized and unsafe use of small unmanned aircraft, mainly close to airports, and we have to make sure how we can prevent that. So one of the main goals of, this is slide 23. One of the main goals of man-unmanned aircraft teaming is to provide a flexible flight operations. Mainly, we have two teams based on different advantage and disadvantage. If we have, one is the UAV is the follower and the manned aircraft is the leader. And the second one, the follower will be the manned aircraft like F-16, and the UAV like Global Hawk Predator is the leader. So in both cases, we should have a teaming law, and also we have to make sure this team is successful. So in this case, we can use the full potential of unmanned systems at an affordable cost, and we have reduced the cost and also the collision possibility. And we can evolve to tactics and techniques and procedures to improve the teaming of man-unmanned teaming. In this case, we have to have different UAV configurations, and also we have to take care of their different characteristics in terms of speed, altitude. For this end, we have critical challenges that has to be identified. For now, I don't know if any successful flight for now. They were coupled, but not completely. So for having man-unmanned teaming, we need new technologies. like computers and sensors and communication systems. Also, on the other hand, we need to have new regulations by FAA. Slide 25. In this flowchart and block diagram, you see a communication between a manned and an unmanned aircraft. You can see they both have the same mission to do one mission. However, they have different trajectories. Trajectory 1 is for UAV. Trajectory 2 is for manned aircraft. In manned aircraft, we have human pilots. In unmanned aircraft, we have autopilot. Both of those are governed by teaming law that we have to develop. And also in the between, you can see T/V and V/T. T/V stands for text to voice, because the autopilot will text and it should be converted to voice to human pilot. When human pilot talks, it creates a voice. There should be a device to convert to text for autopilot and then goes to a signal. So you can see this is just part of the man-unmanned teaming. Number 4, slide, let's see, 26. Formation flight or swarming flight. As you can see in this picture, these are very important and small starlings. They are flying together, 1,000, maybe 10,000, 20,000 of them together, and you will not see any crash, any incident between these flights. So these are intelligent flight, and we would like to be close to these animals and birds. So in this case, we have multi-agent UAVs, let's say 2, 10, 100, or 1,000. And we have 2 main constraints. One is the coordination, X, Y, and Z, and the location. And B is the temporal constraint, which means how we can control the timing of the flight. So in this case, we have leaders, we have followers, also we have reference agents. So we have all of those together for forming a formation flight. You can see in slide 28, I listed here 3 cases. First, in 2016, Intel could have 500 drones. And also in 2018, they went up to 1,200 shooting star quadcopters. It was in Olympic opening ceremony in South Korea. And also in, I think, again, 2019, the record belongs to 2,000 drones light up the sky. And there are a YouTube link here. If I could have my screen, I could go to YouTube and show you this very beautiful scene that all of those are flying together. You can think about how we can manage this number of UAVs in the air. And it has been done for now, but still there are some problems here, because these 2,000 UAVs, they have no relation to each other. They're supposed to follow a different trajectory. And if one of them make a mistake, there should be a crash here. Number 5, next slide. Another important and currently active research project is integration of UAVs into aerospace, which is not happening, which is happening right now. Maybe it takes about 5 or 10 more years at this moment. This is a NASA project. This is a European project and every country project. First of all, we know that the pilot had reported that they had interaction with suspected unmanned aircraft. In 2014 was about 238 sightings. In 2015, it becomes about 1,000. So lots of suspected UAVs. However, FAA is working with several teams, different universities and also industries to develop a framework for integration. At the same time, European Commission and countries also have the same. Slide 31, you will see about 5 different federal agencies in the USA, and you can see their budgets. The largest budget belongs to DOD, about $718 billion. This is for 2020, this just this year. And $100 billion of that one goes to research and development and experiment and flight tests. FAA has about $17.1 billion. And part of that, only $202 $20 million of that one goes to integration of unmanned aircraft into national aerospace. NASA has about $21 billion. About 10% of that one goes to air. About 90% goes to space. Then we have NOAA. Also, we have NSF, National Science Foundation. They have about $7.51 billion. It's interesting to know that if you apply for a grant, only about 21% of the applications will be approved because of the limitations. You can see again, this is the budget allocated to different research projects. In 2019, NASA had launched the final stage of 4-year effort to how we can develop a national traffic management system just for UAVs. Still, we have to wait for maybe 3 more years this to be common. So for the first time, they tried to have a BVLOS, which is beyond line of sight, beyond visual line of sight. And they tried to have multiple UAVs. They took all of those into Reno, it's a city in Nevada. They tried to have authorized individual flight tests, and they go to cities, and they try to have outside the site of operator, how they can do that. This was a project that was done in 2019. At the same time, also European countries also have developed, and they try to minimize the altitude up to 150 meters, and they still are not done yet. Next slide explains, slide 34. Explains our experimental aircraft, 35. They started explains in 1944. So X-1 was a first supersonic aircraft, and now we have X-61. Now they just have the plan in 2019 last year. So you can see we had about 61 experimental aircraft. It's very expensive because it is only one-time use. Why we have experimental aircraft? Because lessons cannot be learned just by textbooks and theories. We have to have some experiments. Some questions cannot be answered by flight theories and also the CFD, computational flight dynamics. These experimental aircraft are done by different groups of Air Force, Langley, and Glenn Research, and they are all working on different aspects. As an example, you can see here that, for example, X-35, when it was done, they committed that one to F-35. And also you can see here, there's a YouTube video that I hope I could show you this one also, that you can see how they develop enabler technologies. One of the driving costs is weight. We have to minimize the cost. One of the lessons we have to learn here, please resist nice to have requirements. So somebody say, it's nice to have this, it's nice to have that, try to not to have those, but they will add to your weight. In general, slide 36 explains have these aspects. They don't have anti-ice system. They don't have lightning protection. They don't have bird strike protection. They don't have any ejection seat because there is no way to have that. Even they could be human inside. They try to have eliminating wind tunnel test. They try to eliminate a structural test just to be faster. In this case, mainly we have a safety factor of 3 for composite structure. Slide 38, you can see here X-48 unmanned aircraft. It has 3 turbine engine. It has unmanned aircraft. And also in this case, you can see they try to have F-16XL, try to have flight tests. And you can see 2 examples. The theory, they predicted this maneuver will create 2.5 Gs, and in practice, the pilot tested 1.8 G. So there was a mistake here in calculation. In another example of F-16, in theory, they said if you have this way or this maneuver, you will have a speed of 199 knots. But in reality, they had 288 knots. Huge difference, more than 30% difference. So they try to have different ways. Slide 39, has just, this is from Wikipedia. You can go and Google all of those. You can see the list of different experimental aircraft or X aircraft. And as you can see, a couple of those are unmanned. X-48, for example, is unmanned. For example, X-47 is also unmanned. So they just continue to do that. These are also done by NASA and Air Force at the same time. Now let's look at just quickly military UAVs. I tried to stop at even in about 5 minutes, just to put some time for question and answer. And so maybe I go to maybe 3 or 4 more slides. Also, we have different and various active research projects on military aircraft. In this picture, you can see 2 aircraft for the same family. In the left side, you can see MQ-9 Reaper. In the right side, you will see MQ-1C Gray Eagle. They are very close in terms of configuration. They both have a fixed landing gear. They both have a turboprop engine. And also, but the difference is in their tail. You can see one of them has V-tail and one of them has inverted V-tail. In this case, also the next slide, 42, you will see that we have X-45A. That was the first one they drive. This is an unmanned aircraft. This is a UCAV, which stands for Unmanned Combat Air Vehicle. This is X-45. This is supposed to go to 35,000 feet with a cruise speed of Mach 0.75. They started in 1999 and they had the first flight in 2003. You can see in the top picture, this X-45 are dropped under the F-18 and there it continues its own flight, and it carries also some ground attack munitions. However, this program postponed, but they went to X-45B in the next one. Another unmanned project is X-47, as you can see in this picture. One in the air, and the second one, lower one, is on the Navy ship. This project also started in 2001, still active project. This is called Joint Strike Fighter. This is supposed to be a fighter, shoot missile, and also it is part of the Navy aircraft. This has a radius and range of 600 nautical miles. And this was also this UAV had a first aerial fueling of in 2015. That was also successful. Let's ask question from the manager. So should I continue or stop here, by the way? Okay, I will continue just a few more minutes, maybe 10 more minutes. Another active research project is automated recovery. We would like to have a recovery for different aircraft. So in this picture, you will see we have 3 groups of automated recovery. First of all, some aircraft can land on their own landing gear, which is called a regular automated landing or recovery. However, some aircraft, they don't have landing gear. So we have to find a way to recover the UAV. In the left, you will see we have windsock. In the middle, you will see we have arresting line. This is for Scan Eagle. In the right side, you can see we have nets. So we have at least three different ways, and these are still in progress. However, we have to have fail safe, which means what happens if there's a failure here, still UAV should be safe. There should be no catastrophic failure here. That's a project. In this case, we have to find out how we can reduce the unsuccessful recovery. And because we have high potential of that, if the speed is not good, they may pass the net, they may pass the hook, and so forth. Also, we have to have the right communication between UAV and also ground station. Otherwise, there will be a failure here. And sometimes there will be a control links with severe between the autopilot and also the UAV and ground station. In this case, we may have a crash here. And in this case, we want the UAV to switch to pre-programmed mode and then have another flight and then reestablish communication and come back. That's again part of the plan, how we can make sure that the UAV is recovered and land. Number 9, fault monitoring, another active research project in both UAVs and manned aircraft and everywhere. How we can monitor if there is any fault here. As we know, we have maintenance scheduled, let's say monthly, let's say yearly or weekly or per flight. And in this case, we need spare parts. If you have unscheduled maintenance, it is costly. It is a cost factor here for UAV operators. And now we have to find out if any part is supposed to fail. This is called fault monitoring, which must be continually conducted on flight, which means there is a box in the UAV that measures and also follows and monitors the safety and the life of every component. If anything is just supposed to fail, they try to find a solution. To prevent any catastrophic failure, they try to detect any fault and system. At the end, if we cannot have a fault monitoring system successfully, we may have human casualties because the UAV may crash into cities or rural areas, and it may crash to a building. So we have to make sure if any part is supposed to fail. For example, if we have a cable, if you have an engine, if you have any screw and nut is supposed to fail, we have to monitor and find that beforehand and have a plan to solve that. How we can predict failure? This is a combination of health or condition, and also how we can do that in terms of forecasting a failure will happen, how we can do that. That's also a research project. If you have a system failure, the UAV must have the capability to reconfigure its own, also replan the flight test and the flight path, and to go to fail safe. For example, if a UAV is supposed to come back to an airport which is busy, but now we have a failure in part, so the UAV should change its own configuration and maybe go back to another airport which is not very busy, not crowded. So in this case, it's very important to monitor the health of every part of the UAV, including engine, including wing, tail. And also in this case, the maintenance is very important. We have to have a pre-plan to maintain the UAV safety and also every part on time. Slide 50, you can see the objects of fault monitoring. What is the objective here? First of all, in this system that we add to the UAV, we want to reduce the unscheduled maintenance. If you're supposed to, let's say, a maintenance of changing, let's say, oil, let's say every 6 months, we don't want to have that every 2 months or at 2 months, for example. We want to have a predict failure. If a screw and nut is supposed to fail, we have to predict that and replace that beforehand. We want to have the condition monitoring, for example, the temperature of the blades, the temperature at different point of the UAV and aircraft. Also, we have to have a better plan for maintenance. And finally, the most important goal of the fault monitoring system is to prevent failure. So as we know in the aircraft, we have lots of failure. Sometimes engine is failing. Sometimes a wire is cut. Sometimes a valve is just not working for fuel. So all of those we may have a problem. To prevent this, we have to monitor all of those. And that also requires some kind of monitoring system. Slide 51 shows you some examples. That's wiring of the electric systems. In 1984, a Boeing 767-200ER had about 150 kilometers of wire. Wow, very long in different locations of one aircraft. In 2012, the Boeing 787 has gone to about 3 times of that, 500 kilometers of wire. And think about if one wire is cut by a mistake or something, what will happen? For the Predator B, which is shown in this picture, which belongs to NASA. This system is equipped with fault-tolerant flight control system, which means they have a triple redundant avionics. For example, for going from a stick to, let's say, elevator, they have 3 wires. If the first wire is cut by accident, the other 2 is active. So this is called triple redundant avionics system that makes sure that at least no failure inside an avionics system. And the last topic is cybersecurity. It's a very important topic because now we are living with the hackers around the world, and UAVs should not be hacked. And this is part of cybersecurity system. As we know that the computer system, we have to protect them from theft, also from damage, to 3 parts of them. One is the hardware, and one is the software, and one is the information. All of those should be kept safe, and they are part of the security of the cyber. Also, we have to make sure that there is no disruption or misdirection of the services that they provide. So we should not allow any aircraft to take the control of our UAV. That's also another important plan. For example, in nuclear power plant, always are disconnected from internet. We don't want to have any connection by outsiders to any nuclear power plant. In lower side, also we have UAVs. We don't want to anybody to have any serious threat to the security of UAV. Billions of dollars are spent on cybersecurity projects around the world, and part of that goes to UAV. One of the solutions I want to mention here is just encryption. We have to encrypt the signal, and this signal should go to the receiver from transmitter, and then when it is received, it is go back to current and regular signal. That's called encryption. That's just one of the important topics in computer science. And now I want to wrap up. In summary, I tried to cover about 10 different active research projects from detect and avoid to cybersecurity to formation flight. I believe all of those are active right now in the US and maybe in different countries. And right now, I think we have about 62 countries are working on unmanned aircraft. And we have more than 1,000 different UAVs are developed and designed. And I think also India also is very active in UAV design and also development. I wish you the best, by the way. I hope you enjoyed this talk and presentation. And I am ready if you have any question, I can answer.
They can type in the
Visual is about maybe 1, 2, 3 kilometers. It's based on the human. We have to see that by our eye. It depends on the color of the sky. If it's cloudy, we have lower, shorter range. If you have just sky, blue sky, we have a longer, because the pilot should see that by eye. I remember in one, we had a UAV, it was white, and then we tried to fly that, it was cloudy. So the pilot missed that aircraft. So aircraft crashed because the aircraft was white and there was also cloud was white. So yeah, that's it's part of the human also, just the capability of visualizing the aircraft. Let's see if I can I see that? I can read my. Top right. Oh, okay. Oh, okay. So should I go down? Let's see. Okay, I can see that. What are some recent developments in achieving self-reliance in autonomous UAVs? That's a big question. I think we are advancing toward the better and better reliance, but still we are not sure about the reliability. I think reliability is not as good as manned aircraft. The numbers are not good, by the way. I think unmanned aircraft is about 1/10 reliable compared with manned aircraft. But in some numbers, I know. Let's see. I think Predator is about maybe 78% reliable.
Okay.
Something around 80 to 90 for some UAVs, and some UAV between 70 to 80% reliable. Still, we are developing, because one of the main important obstacles are autopilot that we still have problem with.
Okay, sir. Another one is from Avinash. How can we make more efficient the performance of solar powered UAVs?
Yeah, I think that's mainly is out of our control, because we are aeronautical engineer or aerospace engineer. That's, I think, mainly part of, I think, chemical science, or I think physics. They have to, I think, design a better, I think, solar cells. That's mainly part of that. I think we need just power in batteries, which is coming from sun. But I think I am not expert on that. But I think we are improving gradually. I know in the US, some companies are coming to our home. They ask us, us to put some solar cell on your rooftop,
Okay.
and you can get power. So that's under development. I know that.
Okay. Another one question from Vinayak. Do you think that transportation with personal drone or jetpack will become a norm in future?
I know there are some active projects in Dubai, for example. They try to have an unmanned taxi, for example, unmanned aerial taxi. But I don't think it's reliable for now. I think at least we need 10 more years to this to be successful. But I don't think anybody in terms of transport aircraft, anybody would like to be a passenger of that aircraft. It's not safe at this moment. But yes. I know that for road, we are successful now. Yes. I know every few years we have Google car is coming to our road. They take picture of the road. Okay. But that's not a joke. That's very serious. I don't think it is happening at least in 10 years.
Okay. So from Saina Ali, how to reduce the UAV radar cross-section area?
Yeah, there are 3 ways to reduce that. I think one is to use a better material. I think one is to use a different structure in terms of having some sharp edges. Also, one is the absorbing material. They can absorb radar systems. So I think there are 3 ways. Again, these are part of the, I think, a structural system that should be done. It's still advancing, and every year we have a better material that we can reduce the CSA of the UAVs. RCS of the UAVs.
Okay, sir. From Rajwansh, future of vertical takeoff and landing UAVs. What is the future of vertical takeoff?
Yeah, right now it's very active. I think every quadcopter has VTOL. Is a VTOL aircraft. You know, it's very successful. In our university, we have a lab, and we have a couple of quadcopters. They can easily take off and land, but I think that's not an issue for now. So because we had technology from past, I think maybe 40, 50 years for now. Okay. And now for UAVs, I think there is no problem with this case.
Okay, sir. Another one, Ramanathan. Which one you would prefer, an UAV or an experienced man flying the aircraft? Which one you will prefer? Whether you will prefer UAV or experienced man?
I think I prefer manned aircraft, definitely. Reliable. We have only one life. So we have to take care of that.
Yes, sir. That's a good answer. From Yash, there is a lot of research in the area of air taxi for transportation. But then why it is not launched in the market? And what is the scope of the future?
Let me see.
Sir, actually, that question is from social media.
Oh, can you repeat the question, please?
He asked about air taxi for transportation. So he's telling that why it is not launched yet, and what is the future of that air taxi?
I believe it will happen. but I'm not sure when. Maybe I think 10 years, 15 years.
Okay.
And I think right now we have some helicopters which is unmanned. I know there are some quadcopters unmanned, but it's still not safe. And think about in the USA, they don't have any permission to fly for now. I don't think they will grant permission for next 10 years.
Okay. So many people are asking the same question. Can UAVs be operated by AI, artificial intelligence? Is it safe for flight?
Of course.
It is safe for flight.
Of course, yeah.
Yes.
I think that's one of the future of control technologies. Yeah, why not? AI is advancing in different ways.
Okay.
I think there are lots of good aspect of AI. Of course, yeah, it will be happening, definitely.
Okay, sir. From Ganesh, what are your insights on Boeing's latest UAV system, Loyal Wingman, and its variable payload capability? Loyal Wingman.
I think Boeing has different projects, and they have teamed with Air Force, I think with some industries. And I think the latest one, I think is 47 still active.
Okay.
UCAV at the moment they are working on that.
Okay.
Still not operational, but they are lots of flight tests every year.
Okay, sir. From Shubham, which guidance system are mostly used in current UAVs?
Guidance system, it depends on the mission. If it is a military, if it is a civil aircraft, they have different case. Also in military, they have different mission. And based on the case by case, I think they will have different. I think in my new book, I have a chapter on guidance system.
Okay.
So based on different, I think mission, we have select which one is the best for that.
Okay, sir. From Ganesh, what is your opinion for using of creative design process in UAV design? New design process.
Let's see.
Yes, sir. It is over in the chat itself.
In the chat.
Suren Ganesh.
Yes, I see that. Yes.
Yes.
Yeah, always I think there are creative design techniques, and I know every year we have new designers that are coming up, and there is no end to this. I think we have lots of new young engineers. They have innovative, and they have a good thought of UAV design. Every year we have new techniques, and we should be surprised to see new design configuration, new design UAVs. I think it's advancing, and every year we have new creative design.
Okay. From Vaibhav, your thoughts on blended wing body aircraft? Blended wing body aircraft.
Blended wing aircraft I think is not successful that much, mainly because of the, I think, safety reason, although it has a lower weight. However, I think because of the safety and stability, I don't think it will become, I think, a conventional aircraft. So at this moment, I think even in a predictable future, we will have a conventional UAV and conventional aircraft for now.
Okay. So one question, what is your opinion on scramjet engine in UAV?
I think scramjet is not very effective in terms of cost. They are very thirsty engine. I don't think they will be used in UAVs for future, except if they want to, I think, carry some maybe rockets to space. They could be used, but I think for air, I don't think they will be successful.
Okay. Sir, I think we can have the last question because we have already spent 1 hour for us. If we are going for high altitude and long endurance, right, sir? So whether we can use airship, or we can go for hybrid, or we can go for UAV itself.
I think airship is not safe, is highly controllable. I think I go for UAV. I think that's very more successful and also more promisable, I think.
So, like if you want to fly for 1 year continuously without landing, then in that case.
For here, I think I go with solar UAV.
Solar UAV.
That is the best. Yes, for high altitude. I think for now we have a couple of experiments for that. I think that will be totally possible because the sun is always in the air.
Okay.
And we can use that. I think that will be the best answer.
Okay, sir. Okay. So thank you, sir. Thank you very much. I request Aishwarya ma'am to give the vote of thanks, and I request the participants to stay there. We will explain the procedure of certificate, participation certificate. So I request Aishwarya ma'am to give vote of thanks.
Sir, thank you so much for accepting our request, and we are very happy to have you with us because it's our pleasure to get a face-to-face talk, like one is to talk with a great writer and the professor and the specialist of aircraft design. So thank you so much, and thanks Kishan for this wonderful platform to create and where people can learn about this entire UAV and they can develop their research work on UAV. Thank you so much, sir.
Thank you for invitation and comments. Yes. And my recommendation: stay at home to be safe.
Yes, sir. Stay safe, sir. Yes, sir. So
very important.
We will discuss further things, how to collaborate with Chandigarh University for some research, and we will discuss in the future also.
Yeah, yes, hopefully.
Sure, sir.
Yeah, but I the best.
Yes, sir. Thank you, sir. Thank you.
Actually, some of our students are doing a project on HALE, high altitude long endurance, and in that they has to fly the aircraft for 1 year. So we are doing it for some competitions. So if we need any help, we will let you know, sir. Please guide us.
If I have time, sure, but sure, I'm very busy.
Yes, sir. Yes, sir.
Of course, sir. And we of course refer your textbooks, all your textbooks, sir, in with us. I used to handle aircraft design project, so I personally refer your textbooks to all my students, and it's really helpful for my students, sir. Very easy to understand. Thank you so much,
sir. Keep writing. Keep writing. Aerospace people are expecting you more from you, sir. Keep writing.
Thank you. But remember, every textbook takes about 10 years to write, so it's not easy to write a textbook.
Yes, sir. Yes, sir. We can understand. We are eager to read your upcoming articles and books also. Thank you, sir.
Thank you very much.
Yes,
thank you. Have a nice evening.
Yes, sir. Sure, sir. Sure.
Thank you, sir. Stay safe.
Thank you. You too. Thank you. Bye.
Yeah.
So, dear participants, right now I will explain how to get the certificate for this lecture. So, kindly please make sure you can see my screen and go through the step-by-step procedure. If you have any query, you can contact us later through our mail, contact@wingsofaero.in. Okay. I hope you can see my screen.
Yes, it's visible.
Right. So go to academy.wingsofaero.in. Right. So use this URL academy.wingsofaero.in. If you have not yet registered, kindly please register by clicking new account. If you have registered, then you can use your username or password. Suppose if you forgot the password, use the forgotten your username or password. You can retrieve that back. So after logging in, you have to find the lecture where it is. Here in the front page, the lecture is available. Recent research on unmanned aerial vehicles. Okay. So what I am showing is here without login. Okay. So what I am showing here is with login. So when you are logging in, it will show the dashboard page. Okay. When you are successfully logged in, it will show the dashboard page. So again, you can go to site home. The same video will be available in our Facebook also. It is already streaming live. So you don't need to worry. If you are missing over here, you can check our channel where you can find the same video and you can collect the certificate later also. So click at the title of the lecture. So you can see the lecture over here, Dr. Mohammed Sadreay. So already we are streaming live. So the live you can see over here also, right? So there is a feedback option. I request all the participants to give the feedback over here, right? So that it will motivate us. And if you want to suggest anything, you can suggest about this lecture or upcoming lectures also. So we will be looking into the feedback strongly and we will overcome that in next session. And after submission of feedback, you can collect your participation certificate just by clicking here. Okay. So if you have any queries, you can just contact us at contact@wingsofaero.in, or you can text to WhatsApp me at in this number 8870705857. I hope you can understand. I hope you have enjoyed the lecture, and I request you all to be safe and take care yourself. We are signing off. If you have any query, you can ask. No issue. If you have any queries, you can ask now itself. No issue. Yes, PPT will be shared in the same link. Soon we will be sharing the PPT. Once we will be getting approval from him, Mohammed Sadreay sir, whether we can share the PPT. So if he said the PPT we can share, then we will share it. Thank you everyone. Thank you for your participation. Keep participating. We will be conducting the lecture in upcoming days also. So please support us. Thank you. Thank you. I hope there is no other questions available. So if you have any queries, you can just go to Facebook. I am sharing the link over here. .com. In this chat box, you can find the link. In that link, you can find the video. Okay. So stay safe. We are signing off.